Hello, my name is John Mwungeli. I'm a material science and engineering student at Texas A&M. I'll be informing you about my project, the temperature dependence of the recombination of vacancies and interstitials. This work was supported by the National Nuclear Security Administration and the online REU program at Texas A&M. My mentors are Dr. Michael Demkovich and Dr. student Esther Liu. Without their technical expertise, I cannot do this research. The major goals of this project are to determine what effect temperature has on the recombination of two types of point defects in crystal structures of copper, vacancies and self-interstitials, and examine how the rates and ranges at which they recombine vary as a function of temperature. So what exactly is a crystal structure, vacancy, interstitial, and self-interstitial? A crystal structure is simply a perfectly ordered periodic arrangement of atoms in space situated at lattice sites. A vacancy defect is a vacant lattice site where an atom would occupy, whereas an interstitial defect is an atom that occupies a space between lattice sites. A self-interstitial is merely an atom identical to atoms of a crystal. This is an illustration of the formation of a vacancy in an interstitial with an energy-carrying particle hitting an atom, leaving behind a vacancy, and the initial knocked-off atom displacing another atom, creating an interstitial. A vacancy and interstitial pair is a common effect of this process called irradiation. The images here illustrate the formation of a vacancy interstitial pair in a silicon structure and its recombination. Both require a minimum amount of energy to take place. A vacancy and an interstitial need to diffuse their structure for recombination to occur. And it's understood that diffusion has a relationship to temperature, and at higher temperatures, atoms experience greater thermal vibrations and diffuse quicker. Examining vacancy interstitial recombination has relevance to understanding how materials behave under irradiation. This is particularly important in nuclear fission and fusion reactors operating at elevated temperatures because a material under irradiation can accumulate defects that can degrade it as a result of vacancies clustering, possibly forming voids or bubbles. These micrographs of stainless steel, aluminum, and magnesium are an example of that problem. Helium is also another issue emanating from radiation. The implications of those things are important in designing materials that could help harness more nuclear power from the energy released from irradiation. The potential is clearly there to resolve the increasing demands for energy and energy challenges, such as electrification, which much of the world still has not acquired, especially in developing regions. Currently, nuclear energy generates just 11% of global electricity, with the absolute majority being from fossil fuels. Nuclear energy is a promising alternative to fossil fuels because, one, it's abundant, two, it doesn't emit CO2, and finally, it can drastically transform life standards for the entire world. To achieve the objectives of this project, we are performing atomistic modeling of vacancies and self-interstitials. We first modeled the crystal structures consisting of 4,000 copper atoms with MATLAB. We defined the basic building blocks of our structure into repeating cubic unit cells with edge or lattice parameter lengths. The crystal structure for copper is face-centered cubic, so we developed the coordinate system accordingly. Then we developed input scripts via Linux interface for the molecular dynamics program LAMMPS that would read our structures and the simulations we want to perform on it. LAMMPS is particularly useful because it allows us to model our structures under specific thermodynamic ensembles, which could be for us modeling experiment-like conditions, controlling for variables like pressure and temperature. We also utilize commands within LAMMPS to compute values for characteristics of our structures and output thermodynamic properties like energy and volume. A potential file for copper made by URI emission is also used in LAMMPS to model the interatomic interactions and calculate energies of our structures that we otherwise wouldn't be able to do easily because of the complexity. Atomi and Ovito are the atomistic visualization softwares that aid us in viewing our structures, defects, and their movements. All of our simulations run on Texas A&M's High Performance Research Computing Center. Here are visualizations of structures with localized defects in atomi. This is one with a vacancy, and this is one with an interstitial. They are made simply by removing or adding atoms and their coordinates within our structure files. We also calculated the energies to form the defects by running energy optimizations on our defect structures. This was done by relaxing the structures so that atoms can move to more favorable positions at lower potential energies. We do this because potential energy is a function of the positions for each atom. We computed in LAMMPS the energy for a perfect crystal structure and derived the cohesive energy, or the energy per atom to keep the perfect structure together, and divided that by the number of atoms. The vacancy formation energy was calculated by subtracting one cohesive energy and the energy of a perfect structure from the final relaxed energy. And the interstitial formation energy was calculated by subtracting the number of atoms including the interstitial multiplied by the cohesive energy from the final relaxed energy. This calculation was also done for the 6 canonical interstitial types seen in copper. The formation energy for an interstitial is more than twice as much than that for a vacancy, and visually it's evident in how much more distortion there is around an interstitial compared to a vacancy. This is an animation of a simulation done on a defect copper structure with a self-interstitial. An isobaric isothermal ensemble was modeled for this simulation, controlling the pressure and the temperature, setting them to 0 pascals and 300 Kelvin respectively. We can see the interstitial migrate along with other atoms due to the thermal vibrations. To study recombination, we first sought to examine coordination number and common neighbor analysis statistics from our simulations. A coordination number is a characteristic of a crystal structure that tells us how many nearest neighbors there are with respect to a central atom. An FCC structure like copper has a coordination number of 12. The introduction of a defect like a vacancy or interstitial to a perfect structure changes the coordination for a number of atoms. When we create a defect in our structure, we no longer have the total number of atoms having a coordination number of 12. A common neighbor analysis is a calculation done within LAMMPS that also describes the local crystal structure surrounding an atom. Within our input scripts, we wrote commands that would compute the number of atoms with the coordination number of 12 and common neighbor analysis value of 1 corresponding to an FCC structure. For our simulations, we took a relaxed structure with an interstitial and then for a few picoseconds brought the structure into equilibrium with the pressure and temperature at 0 pascals and 300 Kelvin respectively. Then we created a vacancy to make a vacancy interstitial pair. Then we ran our simulations for several picoseconds under constant volume and energy while rescaling the temperature to 300 Kelvin. These two plots display calculations from a simulation. We see around 2.5 picoseconds, the number of atoms with a coordination number of 12 converges at 4,000. Similarly is seen with the plot on the right on common neighbor analysis. This is an indication for the mutual annihilation of a vacancy. The coordination calculations were refined by changing the cutoff value to 3.1 angstroms, and the cutoff for common neighbor analysis was based on the lattice parameters of our structures. This is an animation in Atomi for the previously described simulation. Atoms and defects are moving within our structure as a response to temperature and thermal vibrations. The coloring of the atoms correspond to a particular coordination number. As evident, the vacancy and self-interstitial move into positions where they annihilate, and we see that all atoms within our structure have the coordination number characteristic for crystalline copper. Thus far, we have found that analyzing the coordination number and common neighbor analysis values for each atom from the simulations on our structure are useful measures for looking at vacancy interstitial pair recombination, but alone have their limitations at greater temperatures and when the defect pairs are greater distances apart. Ovito is a scientific data visualization and analysis software that offers additional methods in tracking and analyzing defects and their movements, which could be of use. We could also more closely inspect properties like energy. If we are able then to accomplish this, we can compile statistical data and calculate averages for rates and ranges for recombination as a function of temperature.